What specific problem does the thought preference optimization (TPO) method aim to solve, particularly in the context of large language models (LLMs)?
The thought preference optimization (TPO) method aims to enhance the response quality of large language models (LLMs) by teaching them to generate and utilize a thought process before producing a final response. Specifically, TPO addresses the challenge that initial thought generation often underperforms compared to direct responses, as LLMs are typically optimized for immediate output without intermediate reasoning. By employing a preference optimization approach, TPO iteratively refines the model's ability to generate useful thoughts that contribute to better responses, using a reward model to evaluate the effectiveness of these thoughts. This method also mitigates the issue of excessive verbosity in responses through a length control mechanism, ensuring that the model maintains concise outputs while improving overall performance. Ultimately, TPO seeks to align the thought generation process with the goal of delivering high-quality responses to user instructions.
How does the proposed thought preference optimization (TPO) method work? Illustrate the method step by step, from initial prompting to the generation of the final response.
The thought preference optimization (TPO) method begins with a typical instruction-tuned LLM that is prompted to generate its thought process, followed by a response to a user instruction. Initially, the model is prompted using either a generic or specific thought prompt, which helps in separating the thought from the answer by using fixed keywords for easy identification. After generating multiple outputs, the model employs reinforcement learning from AI feedback, RLAIF, to rank these responses using a judge model that only evaluates the response part, ensuring that the thought process does not influence the judgment. Preference pairs are then constructed by selecting the highest and lowest scoring responses, allowing the model to learn which thoughts lead to better responses. Finally, the model is iteratively trained using these preference pairs with direct preference optimization, DPO, to refine its ability to generate thoughts that enhance the quality of its responses, ultimately producing a final output that is sent to the user without revealing the thought process.
Can you provide a simple yet illustrative example of the TPO method in action, highlighting how thoughts are generated and how they influence the response?
An illustrative example of the thought preference optimization (TPO) method can be seen in the process of generating thoughts for a factoid question, such as, which dog breed is the smallest? Initially, the model generates its thought process, which includes evaluating its draft response before arriving at the final answer. This thought generation is guided by a specific thought prompt that instructs the model to draft and assess its response, allowing it to reflect on the question and improve its answer quality. After generating multiple outputs, the responses are scored by a judge model, which only evaluates the response part, ensuring that the thought process does not bias the judgment. This iterative training process helps the model learn which thoughts lead to better responses, ultimately enhancing the quality of the final output provided to the user.
What are the theoretical or practical advantages of using the thought preference optimization method compared to traditional instruction-tuned LLMs that respond directly without incorporating thoughts?
The thought preference optimization (TPO) method offers several theoretical and practical advantages over traditional instruction-tuned LLMs that respond directly. Firstly, TPO encourages the model to generate a thought process before producing a response, which allows for additional computation that can enhance the quality of the final output. This is particularly beneficial as it enables the model to draft and evaluate responses internally, leading to improved reasoning and understanding of the user's instruction. Secondly, TPO employs a preference optimization mechanism that ranks responses based solely on their quality, independent of the thought process, ensuring that the model learns which thoughts contribute to better responses. This iterative training approach allows the model to adapt and refine its thinking over time, ultimately resulting in a performance that surpasses that of direct response models, as evidenced by the improved win rates in benchmarks like AlpacaVal and ArenaHard. Lastly, The ability to hide the thought process from the user while still allowing for interpretability provides a cleaner user experience, aligning with user expectations for concise responses without excessive intermediate reasoning.
How was the effectiveness of the TPO method validated? Discuss the experimental design, datasets used, and metrics for performance evaluation.
The effectiveness of the thought preference optimization (TPO) method was validated through a structured experimental design that involved training a seed model, Llama 3 to 8B Instruct, using two different instruction datasets, synthetic instructions generated from Llama 2 to 70B Chat, and a curated set called Ultra Feedback, which contains actual human instructions. The model was evaluated against a direct baseline model that outputs responses without any thought generation, allowing for a direct comparison of performance. Performance metrics included win rates on public benchmarks such as AlpacaVal 2 and ArenaHard, where TPO achieved a win rate of 52.5% on AlpacaVal, outperforming the baseline by 4.1%, and a win rate of 37.3% on ArenaHard, also surpassing the baseline by 4.3%. Additionally, a fine-grained evaluation was conducted using Ultra Feedback, categorizing instructions into 20 types to assess which benefited most from the TPO method, further demonstrating its effectiveness across various tasks.
What results were achieved with the TPO method on benchmarks like AlpacaVal and ArenaHard, and how do these results compare to the baseline models?
The TPO method achieved a win rate of 52.5% on the AlpacaVal benchmark, which is a 4.1% improvement over the direct baseline and a 27.6% increase over the seed model. On the ArenaHard benchmark, TPO reached a win rate of 37.3%, outperforming the baseline by 4.3%. These results indicate that, after several training iterations, the TPO model not only matched but also surpassed the performance of the direct baseline, which was initially better due to its instruction-tuned nature. The TPO model's performance improvements were particularly notable in later iterations, demonstrating its ability to adapt and utilize thought generation effectively. Overall, TPO positioned itself as a competitive model, achieving results comparable to much larger models like GPT-4, despite being significantly smaller in size.